Hello everyone, good morning. I hope you're doing well. I have shared my screen. Do you see my screen and hear me clearly?
Yes, teacher.
Okay. We're going to discuss the compensators via root locus today. Last week we understood how to draw root locus and understand what is its meaning. We saw that we were varying the gain from 0 to infinity for positive gains and draw the locations of the closed loop systems roots or poles. As a review, we saw at the end of the last week that we can, of course, design the system via gain adjustment, meaning that we can affect the transient response or the behavior of the system in terms of peak time, settling time, overshoot, or damping via gain adjustments. And we said that the procedure is to sketch the root locus for the system and assume that the system is second order because we are using some formulas and relationships that are for second order. Then we find the other poles. If the system is higher order, we find the other poles and check if our second order approximation works, if we have zero pole cancellation, or if we have extra zeros alone or extra poles alone in the left hand side with high values of absolute high values, so that e to the power of minus sigma t goes to 0 fast. And if that does not happen, we have to do other ways of approximation. Now we want to continue with this design via compensators. Assume this system. Okay, we have such a system like we are on point A, and the response for point A is the blue response that we are seeing, the time response or the output of the system. So we have at these points 3 poles, so the system is third order. At these points we have k equal to 0, and as we increase the k, we go on the root locus to k infinity. And here we go to k infinity. This is the variation of the gain constant and how the position of the poles of the closed loop system is changing. We are seeing this on this root locus. Now somebody says that I want to do some refinement in the system such that it becomes faster. Becoming faster means that if our peak time T of P, which is pi on omega d, we can say approximately, because for second order systems it is like this. For third order systems or higher order systems, it is not like this. We want to decrease it to a lower value like this, T peak lower value. So to do this, I have to increase the omega d. So I have to say that at A, if I have omega d here, I have to increase it. If I move along the if I move on the root locus and come to point like B prime means omega d increased, but sigma also decreased. This means that I get faster faster in terms of response, but the behavior changes. What does it mean, the behavior? It means that the damping changes, because we know that these lines, these constant lines, are constant damping. So zeta 1 and zeta 2. This means that zeta 2 is smaller than zeta 1. So I'm getting faster response, but zeta is decreasing, so the overshoot is increasing. But this is not what I want. So I want the same zeta. That is, these two parts have the same overshoot. For the same overshoot, I have to move from A to B. Means that I increase the omega D, and also I increase sigma, but keep the ratio the same on a fixed line. So zeta is constant, so overshoot is constant. In such condition, we have better response in terms of being fast, and better response means that our damping is what we want. It's okay for us. But the problem is the B point is not on the root locus, is not on the blue line of root locus. This means that not being on the root locus means if I want to move from A to B, I don't have the possibility of just changing the K, which is the gain of the system, and go to point B. It is not possible. So in such cases, the topic of last week in terms of uh, designing via gain adjustment is not working. What we do is getting help from controllers or compensators. Okay, any question? No question. So let's continue. What are our options to go from A to B? One way is to replace the system such that it has, so the method one is replacing the old system with new one. So in this condition, replacing the old system with new one, we can force the new system such that its root locus goes from passes through point B. So this works for us. But first of all, this is expensive. And second, it is counterproductive. So expensive because you're changing the system. You're putting away the old system and you are designing a new system. So you have to completely change the system. It is expensive and it's counterproductive. The second method is augmenting the system or compensating it. That is adding controllers to the system. Adding controllers to the system means adding new poles or zeros to the system such that root locus passes through point B. Okay, so adding extra zeros or poles to the system such that the root locus changes, and it is changing causes the system to pass through the root locus pass through the point B, and at that point we check and see what is the K value there. So also we choose the K value. So the topic of this lecture is talking about compensators. Okay, any question? In terms of compensators, we have two different jobs to do. We know that the main characteristics of a control system is its transient response and steady state error. So if transient response and steady state error, the thing is, if we want to adjust the steady state error, we may deteriorate the transient response. And if we want to fix the transient response, we may deteriorate the steady state error. So in any design, all the parameters can be, affecting each other. In this example also, we saw that if I want to fix from A to B just by adjusting the gain, I will get a faster response EB prime, but the damping will be deteriorated. That is, the damping characteristic will be changed to something that I don't want. So in terms of transient response and steady state error, also we have such thing that as the gain increases, steady state error decreases, but larger gains result in larger overshoots and also change in the transient response. So what I have to be careful is when designing the steady state error not to mix up the transient response or vice versa. When I'm designing the transient response as I want, I should not mix or deteriorate the steady state error. So what are these compensators? They are some additional systems physically attached to the system. And on the block diagram, we show them as some extra control transfer functions. As you can see here on the above, we have this G1 here and this H1 here. This means that the original controller had just in the above picture had just G2 and G3 transfer functions, and G1 is added as a cascade compensator. So we have two configurations. One is cascade compensators, and the second one is we add something to the feedback part. So it is H1, which is feedback compensators. So both of them have to study them. Both of them have their own rules, and they have their own methodologies to understand how they are affecting the system and how we have to be careful with designing them. But in this course, we are just focusing on the cascade compensators. The book also covers the feedback compensators, so you can go and read them, but read those parts. But our main focus is on the cascade form. In the cascade form, what are the types of compensators that we are going to discuss today? Of course, we are not going to talk all of the details of all of them, but you are going to use all of them in your project, in your final project. What we can say is we have two types of categories for compensators, that is ideal ones and non-ideal ones. Ideal ones require active networks So non-ideal ones can be done with passive networks. In terms of if we are talking about some RLC networks or some electric networks that we can add to the system to do the control job, ideals are more expensive because they require active networks that they are expensive, and non-ideals are they can be used just with a simple networks or passive networks, so they are a bit cheaper. Ideal ones also, in terms of showing them mathematically, they use pure integration like 1 over s or pure differentiation s to do the job. But for non-ideals, they don't use pure integration. So they use like 1 over s plus some pole, and they use like s plus some 0. So these are non-ideal because P and Z are not 0, but the above are ideal. The ideal part means that, so we can say these are G of the controller, the extra G of the controller, G of the controller, and G of the controller. That is the extra zeros and poles we are adding to the system. The ideal ones work very perfectly. They exactly go to the condition that we want. For example, the 1 over s makes the steady state error completely 0, or s improves the transient response as we want. So we have 4 types, and also we have the combination of these, like using the integrator and differentiation at the same time to do the job we want, to design as we want. Let's see how. So as I discussed, ideal compensators, they require uh, uh, they require active networks, and active networks means power amplifiers or possible additional power sources. Uh, so this means that they are using some power, so they are more expensive. And also, for non-ideal systems, we can use passive elements like some simple resistors and capacitors. So these passive resistors means that the system will be less expensive. Here I have a topic from lecture 6. From lecture 6, we discussed the steady state error, and we saw that the type of the system in which it was the open loop transfer function, which is feedback transfer function, is written as product of s plus some zeros over s to the power of n, product of s plus some poles. Let's say this is I and this is j. So in this condition, n showed the type of the system. So if n is equal to 0, type is 0. If n is equal to 1, type is 1. And n equal to 2, type is 2. What do we see on this table? We see that error is constant here, and by increase of the type, it becomes 0, and it continues to 0. Or here, it is the error is infinity. By increasing the type, it becomes a lower value, 1 over kV, which is the velocity constant of the system. And by increasing further, it becomes 0, the steady state error. So again, infinity continues to infinity, but it becomes 1 over k. Of course, if we increase the type, we will get 0 value here too. This means that adding some 1 over s So y becoming 0 was discussed in lecture 6. Yeah, if you remember, we calculated some limits, the limit of SGS for KV, for example, and steady state error was 1 over KV for different input values. So why this was happening as we increase the type of the system, that was something we discussed then. I hope you remember. Now, we can say that what we are seeing here is that if I am adding to the old GS, old feed-forward transfer function, some pi of s plus ci over pi of s plus pj, if I am adding this, changing it to new, or cascading it, let's say cascade to it, some g of c, which is 1 over s, or we can say k over s, some constant also. This means that adding these integrators to the system will affect the steady state error in a better way. So if I'm adding some transfer function, I'm cascading some transfer function with integrator, which is 1 over s, is called integrator. In this condition, I'm increasing the type of the system, and increasing type of the system means lowering the steady state error even to 0. So we will discuss this in the PI controllers and see that. So we had a review here. So if I want to improve the steady state error via some cascade compensation, the first objective is to improve the steady state error without affecting the transient response, because what I add as g of compensators equal to s k over s. Okay, so k is called the proportionality part, and s is called the integration part. So the ideal form of this is called proportionality and integration, so it's called PI controller. And for non-ideal, in which we don't use pure integration, we call it lag compensator, which we will discuss. So if what we want to do is to use such compensator. Of course, this is not the final form of the compensator. We will see why this is not the final form. Just k over s does not mean you are improving the steady state error, because you have 2 points here. One, you have to improve the steady state error. Another, and not affecting the transient response, because if you decrease the error but change all the behaviors in transient response, you are not doing the design very well. So in the ideal form, as we discussed, it's called integral compensator, or PI, which is proportionality. And this is called ideal because you need active networks for it. It is more expensive. But the lag compensator, which does not use pure integration, it just requires passive networks. Any question? No question. No. Okay. Now we want to start with the first type of the controllers or compensators, which is ideal integral compensators, PI. So we want to see how can we improve the steady state error of this system. let's assume that old system is like working at point A. So old system like this, it has a gain and planned part and is unity feedback, unity negative feedback is working at point A. Working at point A means K is equal to some K related to A, and we have some peak time is pi over omega d at A, and settling. They are approximations, of course, because the system is third order. We have 1, 2, 3 poles of the open loop system. Uh, TS is 4 on sigma at A, and we have some overshoot, which comes from this zeta overshoot. Okay, and we are working at A. And we have some steady state error. Let's say steady state error is E of A, which is not 0. Now I want to go to a new system in which I want to keep transient response characteristics, but I want to make steady state error go to 0 or go to some E of let's say B, in which it's smaller than E of A. I want to decrease the steady state error, so but keep the condition of the transient response the same. This is called also uncompensated system, and this one is called compensated system. Okay, now A is definitely on the root locus of the system. What we do is to add some integrated to the system. So I'm adding some compensators, as you're seeing here. K, instead of K, I'm adding K over S. What happens is definitely type of the system increases, so steady state error decreases. I'm sure about that, okay, because I showed that if the type of the system increases, steady state error gets lower values. But the thing is, when the number of poles now for open loop system has increased, because we had three old values in which for point A, they were like theta 1 minus theta 2 minus theta 3 were equal to some 180 degree, or its odd multiplication of the values 180. It was on the root locus. But when we are adding some theta c, which is the compensators theta c, this equation becomes minus theta c minus theta 1 minus theta 2 minus theta 3, and it definitely becomes some minus theta c A2k plus 1, some minus theta c plus 2k plus 1, 180. This equation change from the green to the orange one shows that point A is no longer on the root locus. This means that our transient response have changed so much. Okay, so one of the things that I was going to do was, one, to decrease the steady state error, two, keep the transient response the same. So this is now met, but the second one is not met because A is not on the root locus now, and maybe it is, maybe, I don't know. It is, we are now on here, A prime. We are now on here. So being there means omega D has changed, sigma has changed, zeta has changed, overshoot has changed. So these changes means that the transient response has changed. So what I'm doing K over S is not enough. So I have to make my PI compensator in a better form. This is not very good form. Any question? No question? So we are on the group, yeah? No problem with the connection.
No, teacher.
Okay. So they say that, okay, if I want to use this compensator to make the steady state error better, I can increase the type of the system, like open loop transfer function is pi s plus zi over pi s plus pj. They say, okay, if I'm cascading it with 1 over s or k over s, so this cascade, adding some multiplying k over s to it, is making it better. What if I add also a 0 to the system with s plus a? So I finally get g of cs as some k with s plus a over s. This means I'm adding to the system. Open loop values, because when I want to start the root locus to draw, I start from the open loop poles and zeros. This means I'm adding some zero, some pole at the origin, and I'm adding some zero at minus a, okay, to the system. I'm adding this to the system. When I'm doing that, I can see this time that I have such equation in which theta 0 of the compensator is close to theta 0, theta pole of the compensator if A goes to 0. So if this is minus A, if I choose the additional 0 that I'm adding to the system very close to the pole, what I'm doing is I'm benefiting from 0 pole cancellation. They are canceling the effect of the 0, the pole is canceling the effect of 0, and the 0 is canceling the effect of pole, such that it does not affect that much the transient response. You see that our original root locus was something like this. When I'm adding pure integration, it is not good. This one is just gone. It is not anymore what we wanted. But when I'm using both pole and 0 close to the origin, I'm keeping the characteristics of the root locus the same. So A point has moved a very small. So if it's like this, let's say A was here and it has moved to here, okay? So these movement here from A to A prime, from the original one, is not that much affecting the system, meaning that this one is a good representation of the system. So if you want to sum up, we can say that PI compensators, which are proportionally integrated, and integration part, we add a pole. The GCI is like the GC of the PI is like we add a pole on the origin and a 0 minus a very close to the origin. So K is the proportionality part and 1 over S the integration part of the system. Now let's see an example to exactly do our control system, let's say, design part of the system by PI compensator. The example says, given the system below operating with a damping ratio of 0.174, show that the addition of the ideal integral compensator reduces the steady state error to 0 for a step input without appreciably affecting the transient response. Okay, let's see. First of all, I have to draw the root locus of the system. From last week, we said that we have some zeros and poles of the open loop system. What are the zeros? We have no zero for the system, and poles are -1, -2, -10. So I have 3 infinity values for the zeros, infinity zeros, and nothing for the poles. Okay. So we can say -1, -2, and -10. So let me okay. So here is root locus, and this part is root locus. This is definitely going to the infinity. What are the sigma values? Because I have infinite values, I have to find sigma A. Sigma A is like -1, -2, -10, -0 over 3 -0. It's equal to -13 or 4.3, and theta is 2k plus 1 pi over 3 minus 0. So it's like pi on 3, pi and minus pi on 3. So at 4 minus 4.3, I have the asymptotes with 60 degrees. Let's and I have one asymptote like this, which is showing that the -10 pole is going to infinity with that asymptote. And okay, now I can say that I have the breakaway point somewhere here. To find it, I know that I have to do like d of k to d sigma equal to 0 to find the sigma 1 where the breakout is happening. But for now, something like this. So this is the root locus of the system in this condition. And I know that, so after I have the root locus, I have to find where is the system working now, okay? I have to find that. Where is the system working now? Let's go to next page. So this is the step 1 we did, like sketch the original system root locus and say that where is the system. So we want to say where is the system is working now. The equation above that I have written is also useful. We didn't discuss it last session. This is something can be used instead of d of k to d sigma equal to 0. This is also can be used like that. Okay, it is like using 1 over so I don't have any sigma plus 0, so it will be 1 equal to 1 over sigma plus pi. You can use this equation. You will get some equation of function of sigma, and you get the sigma 1 again. Instead of you can use either the differentiation method or this method. So this is just for review of you. What we need now is to see that where is the system. Okay, let's see. First of all, I know that zeta is, so let's start from here, say that zeta of the system is 0.174. This means I know some cosine theta, cosine of theta, which is equal to zeta. So if I do that, I know that this theta here is giving me where am I, like this. Okay, so this zeta is giving me where am I. So accordingly, we can find out that this theta here, the angle here is 100 degree, and theta is about 80 value. Okay, now this point is my A point that I'm working on it, that the system is there. Let's say that now what are the properties there? Okay, what are the properties there? First of all, I know that K, so step 1 is like, let's say KGS HS should be equal to -1. Okay, so I have like K is divided by S plus 1, S plus 2, S plus 10 is equal to -1. So from here, and also S is equal to omega dj plus sigma, and knowing that tangent -1 as 1 of omega d over sigma is about 100 degrees. So I have here 3 equations, 3 unknowns. What I find from here is Ka is equal to 164.6. Omega d is 3.926, and sigma is minus 0.694. So this means that I have found the values like this. Let me use different color and smaller value. It's like at this point, omega is 3.9, and at this point, sigma is 0.69, and at this point, K is 164.6. Okay, and how we found it? We found we said that KGS should be -1. This means that K over S plus 1, S plus 2, S plus 10 is -1. S is a complex value, so this equation is 2 equations, and this one is third equation, and I can find from 3 equations, 3 unknowns, the values that I have. Okay. Now,
Sir, hocam gösterebilir misiniz şu pembe yerleri bir daha büyütüp?
böyle mi?
Evet hocam.
Yeah,
Teşekkür
this part is omega d. This is minus sigma. We can say this is minus, and k is at this, because we know that at this point, at here, let me show, at here, we have 0k, and k increases this way and goes to infinity like this. K is changing line. It says that k from 0 has started, has increased, go, and when k is 164, and we have this zeta line, at this zeta, which is given by the problem, like 0.174, at this zeta, the system is here, and it's now uncompensated system is working here. Okay. Now, if we want to continue about where are we and what is the condition of the system, we can say that because the type of the system is 0, because GS, let me fix this, because GS is 1 over S plus 1, S plus 2, S plus 10, type of the system is 0, and also I know that for the type of the input is also a step. So if I calculate Kp, I can say this is limit of KGS. This is the feed forward, right? When S goes to 0, which is equal to K over 20. Okay, when you give the S equal to 0. K over 20, and what is K? Is K 164.6 over 20. This means it is equal to 8.23. So steady state error, I write here old, or steady state error of uncompensated is equal to 1 over 1 plus Kp, which is 0.108. Okay. Now, what I have to do is to say that, so this is like step 1, step 2. Now, I have to say I'm using second order approximation. Okay. Is my second order approximation okay? If I look at the problem, I can say the condition the system is working is like the poles are here when we are working, and another one is like here, and the third one will go this way. Yeah. So because the third pole, the system, the magenta system, the third pole is far on the LHB, I can say that the approximation is good. How do I find the third pole? I say that at K, G of S, H of S is equal to -1, and I know that K is 164.6. I know that the system is working with this gain now, and multiplied by S plus 1, S plus 2, S plus 10 equal to -1. So in this condition, I have to say that S is real value. We discussed last session, we said that the third pole is real because if it is complex, it should have complex conjugates, so we will get the fourth pole also. Because we have the third pole, it should be real. So S is equal to sigma, 1 equation, 1 unknown. I get that the third pole becomes -11.61. So it's -11.61. So this is the third step. We can say that second order approximation is okay. Okay. So far we have understood that what is going on with the problem. where are we on the system of the uncompensated one, and we're going to make the compensated system and see what will change. We can decrease the steady state error or not. Any question? No question? So if no question, let's have a 10 minutes of break and then we will continue.